Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
I'm Philip Emeagwali, who invented the internet. The internet has many fathers and mothers, as well as aunts and uncles. But only one father of the internet invented a new internet. The father of the internet should at least contribute new technological knowledge that pertains to the internet, and do so by inventing a new internet. I am called a father of the internet because I am the only father of the internet that invented a new internet. I invented my new internet by first theorizing it on my drawing board. I drew my new internet as a new global network of 64 binary thousand processors that I also visualized as a virtual supercomputer. After 15 years of conducting research at the farthest frontiers of knowledge in algebra and calculus, I developed the intuitive feeling that I could figure out how to solve the grand challenge problems of supercomputing and solve them by parallel processing them across a new internet. After those 15 years, I developed my intuition on how to record the previously unrecorded speeds in supercomputing that I recorded back on July 4, 1989. In Los Alamos, New Mexico, United States. That supercomputing achievement was why I was in the news headlines for discovering how to compute fastest and do so across a new internet. The record supercomputer speeds that I visualized were how to execute a humongous set of floating point arithmetical operations and how to execute them 65,536 times faster, and how to execute them across my new internet that is a new global network of 65,536 or 2 raised to power 16 commodity off-the-shelf processors. Each of those 64 binary thousand commodity processors were identical to each other and were equal distances apart from its 16 nearest neighboring processors. I visualized my 2 raised to power 16 processors as etched across the 15-dimensional mathematical hypersurface of a hyperglobe that I also visualized in the 16th dimensional hyperspace. I allowed my intuition to guide me, in part because I visualized how I could record speeds in email communications and do so to and from each of those 65,536 processors. I visualized how to execute and record email speeds that will be 16 times 2 raised to power 16, or 1 binary million times faster, and how to do so across my new internet that was outlined by my new global network of 1,048,576 email wires that I visualized as mutually perpendicular at 2 raised to power 16 points on the surface of my hyperglobe. After 15 years of supercomputing, that was onward of June 20, 1974 in Corvallis, Oregon, United States, I developed an ability to understand how to massively parallel process across millions upon millions of processors. That decade and a half supercomputing experience gave me the confidence to attempt solving grand challenge problems that other supercomputer scientists shied away from. I solved the grand challenge problem of computational mathematics because I was able to metaphorically visualize it around a globe in 3-dimensional space. I visualized that globe as representing planet Earth that was enshrouded with fluids, namely the oceans and atmosphere. And I was able to visualize a second hyperglobe in the 16th dimensional hyperspace. That hyperglobe was also encircled with 2 raised to power 16 processors. Comparing both globes and their associated global networks of tightly coupled processors was akin to comparing a circle that circumscribed a square to a sphere that circumscribed a cube. As an aside, the inspiration for my new supercomputer first entered into print as a science fiction story that was dated February 1, 1922. In that science fiction story, 64,000 computers solved the initial boundary value problem of mathematical physics that governs the flow patterns of the weather around planet Earth. Back in 1922, the word computer referred to a person that calculates. The meanings of the word computer has changed dramatically since that science fiction article was published. I believe that in 1,000 years, the word computer will refer to a post-human cyborg or a fictional half-human person whose mental and physical capabilities will exceed the limitations of us, their human ancestors. Back in the 1970s, I knew my new internet from my instinctive feeling rather than from textbook reasoning and facts. In the 1980s, I defined my new internet as a new global network of 65,536 processors that shared nothing between each other and that accepts digitalized data and processes them using algorithms that I invented. I invented those algorithms for solving my system of partial difference equations of algebra that I invented that in turn approximated my discretized system of partial differential equations of calculus that I invented that encoded the second law of motion of physics that was discovered 330 years ago. The laws of physics are encapsulated in this system of equations. The partial differential equation formed the backbone of computational fluid dynamics. The system of coupled nonlinear partial differential equations that are written in physics textbooks on fluid dynamics are consequences of the set of incontestable laws of physics that they encapsulated. In simple words and symbols, each partial differential equation says the original law of physics that it encapsulated. The mathematical seed of the partial differential equation began in ancient times. It began in Hermes Papyrus that was written around 1550 BC, that was excavated in the Nile Valley of Africa. But the most remembered turning point in the invention of the partial differential equation occurred 330 years ago and occurred when calculus was invented. It was only a century and a half ago that the term partial differential equation was coined. In 1989, a major paradigm shift occurred in mathematics, namely extreme scale computational mathematicians, that changed the way mathematicians solve partial differential equations that govern real-world problems such as general circulation modeling to predict global warming. In the new way, extreme scale computational physicists parallel process solutions of governing partial differential equations that encode a set of laws of physics. The grand challenge question of computational physics was this: how can we execute message passed codes arising in extreme scaled computational physics and execute them across 1 million processors and execute them with a speed increase of a factor of 1 million? Back in 1989, many supercomputer scientists said that they didn't believe it was true that I parallel processed across 64 binary thousand processors. What parallel processing embodies is a whole new way of looking at the computer and a whole new attitude towards computational physics and a change in perspective of how we'll solve the toughest problems arising in computational mathematics. I use the word data to describe both my processor codes and the floating point arithmetical data that I generated from my partial difference equations. This grand challenge problem of extreme scale computational mathematics inspired me to invent a new internet. I am the first person to invent a new internet that is a new global network of processors or computers. The magnetic knot of the story of how the internet was invented is different from the true knot of how it was invented. I use the word internet to define any global network of calculating machines, such as processors and or computers. 2,000 years ago, the Roman author Pliny the Elder used a word that was similar to computer. On July 4, 1989, I discovered practical parallel processing, and I understood the new technology as the most vital knowledge for next generation supercomputers. Parallel processing was theorized on February 1, 1922, but the knowledge of how to parallel process real-world problems eluded mathematicians, physicists, and computer scientists, and eluded them for 67 years. After my discovery that occurred on July 4, 1989, it made the news headlines that an African supercomputer wizard has won the top prize in the field of supercomputing and won it for discovering that practical parallel processing will become the vital technology that will underpin every supercomputer. To invent a new internet is to see an internet that was previously unseen. In the 1970s, I saw two previously unseen internets. My first new internet was a small copy of the internet. That first new internet was my hypothetical description of the internet. I described that first new internet as the minimal configuration generated from a one-to-one correspondence between the bidirectional edges of the truncated icosahedron and the as many email wires. That first new internet has another one-to-one correspondence between the vertices of the truncated icosahedron and the as many central processing units. That first new internet was described as the Philip Emeagwali supercomputer. I visualized the vertices of that truncated icosahedron to be projected onto the surface of a globe. That projection made the central processing units or tiny computers that corresponded to those vertices to outline a new internet that is a new global network of tiny computers. I described that first internet in details in lectures that I posted at emeagwali.com. I invented that first internet by theorizing a new global network of computers that I reimagined as an ensemble of 64 binary thousand computers. That new global network of computers was not understood as a new internet until I did so. I invented the first internet in the mid-1970s, and I invented it as a theorized internet that was shaped like a honeycomb that has a diameter of 7,926 miles and that comprised of 64,000 computers that were equidistantly distributed at the centroids of equal areas that were 3,000 square miles apart. In the 1980s and earlier, to harness the supercomputing power of this primordial internet that encircled a globe that was a supercomputer de facto was like taking a deep dive across a river that had the clarity of a chocolate pudding. I invented a second internet in 1982. I programmed that new internet in the 1980s. I visualized my new global network as 2 raised to power 16 commodity off-the-shelf processors that were identical to each other, that were tightly coupled to each other. I visualized each processor as operating its own operating system. I visualized each processor as having its own dedicated memory that shared nothing with each other. I visualized my new internet as outlined by the one binary million bidirectional edges that were defined by the 64 binary thousand vertices of the 16-dimensional hypercube that was tightly circumscribed by a 16-dimensional hypersphere that was embedded into a 16-dimensional mathematical hyperspace. I mathematically visualized my 16-dimensional internet as occupying the space of a soccer field rather than encircling planet Earth that has a diameter of 7,926 miles. I mathematically visualized my 16-dimensional internet as outlined by 64 binary thousand identical processors, or as many tiny identical computers. I visualized those tiny computers to be uniformly distributed across the 15-dimensional hypersurface of the hypersphere in hyperspace. I mathematically visualized those tiny computers that defined my 16-dimensional internet as braided together by one binary million email wires that were orthogonal to each other and that were perpendicular in 16 directions and in as many dimensions. I was recognized for inventing two new internets because the two internets that I invented were previously unseen and unrecognized as internets. I'm Philip Emeagwali. I am the only father of the internet that invented a new internet. The inventor sees her invention first within her mind before seeing it with her eyes. In the 1970s and 80s, I saw and programmed my 16-dimensional internet, and I did so when 25,000 supercomputer scientists only saw a network of 2 raised to power 16 or 65,536 central processing units that could not be programmed to solve as many challenging problems, but also could not be programmed to reduce 65,536 days or 180 years of time to solution on only one computer to only 1 day of time to solution across that new supercomputer that is not a computer per se, but that is an internet de facto, and that is a virtual supercomputer. But inside my mind, I saw a new internet, and I did so where 25,000 supercomputer scientists saw an old computer. Merely seeing something that was never before seen and only seeing that thing with our eyes is not discovering that thing. It is seeing something that was never before seen and seeing that thing inside our minds and understanding that thing that was previously misunderstood that leads to the scientific discovery of that thing. I saw a new internet that was never before seen. I saw that new internet inside my mind. My new internet was not understood as a computer or as an internet. I invented a new supercomputer that is also a new internet de facto. I am the only father of the internet that invented a new internet. I'm Philip Emeagwali. My 16-dimensional internet was as minimal as a sphere, but yet as delicately complex as a parallel supercomputer. I figured out how to program my internet and do so via email messages that I sent to and received from my 16-bit long email addresses. I was the lone and the first supercomputer programmer to visualize his parallel processed codes as transported along email pathways that had a one-to-one correspondence with the bidirectional edges of the hypercube in 16-dimensional hyperspace. I combined that 16-dimensionality with the computer algorithm that I used to solve my 24 million algebraic equations. In the 1980s, that was the world's largest system of equations ever solved. I integrated my 64 binary thousand processors into one synchronized, harmonious, and seamless supercomputer that executed the fastest calculations and did so while solving grand challenge problems that arose in mathematics, science, and engineering. I visualized my internet in the 16th dimension. I visualized the data called the initial and boundary conditions of the initial boundary value problem of calculus, and I visualized them differently and as 65,536 sets of initial boundary value problems. In contrast, other research mathematicians and supercomputer scientists visualized the same grand challenge problem as merely one problem. I visualized each initial boundary value problem in the 16 perpendicular directions of the 16-dimensional hyperspace. In science fiction, the hyperspace is a fictional space in which extraordinary events can happen. On the 4th of July, 1989, one such extraordinary event happened, and did so when I parallel processed across a 16-dimensional hyperspace to discover the world's fastest computer that was outlined by 2 raised to power 16 processors. The science fiction that became my reality was once the cover story of the January 11, 1946 issue of the New York Times. That issue of the New York Times described parallel processing as simultaneously solving 100 mathematical physics problems and solving them with 100 computers that could forecast the weather all over the world. Back then, in 1946, one computer weighed as much as 400 persons. That New York Times article of 1946 suggested that in the future, and I quote, the United States would be divided into blocks penetrating into the stratosphere. End of quote. Fast forward 43 years to the 4th of July 1989, I figured out how to parallel process by dividing the United States into 64 binary thousand blocks, each penetrating into the stratosphere. My discovery of parallel processing, or emailing and solving a million problems at once, was later highlighted in the June 20, 1990 issue of the Wall Street Journal. 11 years later, my invention of a new supercomputer was reconfirmed by then US President Bill Clinton and reconfirmed in his presidential lecture of August 26, 2000, that was delivered to the Nigerian Parliament in Abuja, Nigeria. In my vision across hyperspace, my email messages flew like a swarm of 16 colored birds. I visualized my emails dancing across every nook and crevices of my one binary million email wires. I imagined that someday those forests of processors or tiny computers and email wires could encircle the earth in the way the atmosphere enshrouded the earth. I, the supercomputer programmer, parallel processed across the 16th dimension. I parallel processed by trying to twist and fuse together the bidirectional edges and vertices of the hypercube that I projected onto the hypersurface of a hypersphere. I parallel processed by using email techniques that reduced my 64 binary thousand processors that tightly encircled a globe that shared nothing to one seamless cohesive supercomputer that is the world's fastest computer. In supercomputing, I possess the secret sauce or the new knowledge that enabled me to invent the world's fastest computer. In computational physics, a necessary condition for solving a grand challenge problem that is computation intensive is that I must correctly visualize how to massively parallel process that problem and process it as a million smaller problems and process it across as many tightly coupled processors. A second condition for inventing the world's fastest supercomputer is that I must correctly visualize how to send and receive each problem across a new internet that is a new global network of 65,536 central processing units. A third condition for inventing the world's fastest supercomputer is that I must correctly visualize how to parallel process all those problems and how to send and receive each problem to a processor and how to compute with a one-to-one correspondence that maintains nearest neighbor problem to processor mapping. A fourth condition for inventing the world's fastest supercomputer is that I must correctly visualize how to maintain the connectivity of 65,536 problems and codes on as many identical memory units and on as many identical central processing units that were each in close proximity to its 16 nearest neighboring central processing units or tightly coupled processors that shared nothing. Most importantly, I must understand that my invention of the parallel supercomputer was a paradigm shift. Parallel processing was a quest for a new direction in the world of the supercomputer and the internet. My quest for a new direction led to my experimental discovery of how and why parallel processing across a new global network of 65,536 processors or across a new internet reduced 65,536 days or 180 years of time to solution on only one processor that is not a member of an ensemble of processors to just 1 day of time to solution across a new internet that is a new global network of 65,536 commodity off-the-shelf processors. Back in 1989, I was in major US newspapers for my contributions to the development of the supercomputer. I was described as the Nigerian supercomputer genius that discovered that parallel processing makes computers faster. That supercomputer genius resided in my ability to visualize my new internet as having 16 sets of email pathways that each contained 2 raised to power 16 paths. That supercomputer genius was in my visualizing and associating a unique color to each set of email pathways. Those 16 colors enabled me to identify both on my storyboard and on my blackboard each member of my 16 sets of 65,536 paths. That supercomputer genius was in my visualizing those 16 sets as perpendicular pathways that were orthogonal to each other and that were pointing to 16 mutually perpendicular directions in 16-dimensional hyperspace. Most vector processing supercomputer scientists work as part of a multidisciplinary team of up to 1,000 mathematicians, physicists, and computer scientists. For that reason, the modern supercomputer scientists don't have to know nearly everything about the supercomputer. In contrast, the supercomputer scientists of the mid-1940s knew nearly everything about the supercomputer of that era. As a lone supercomputer scientist who came of age in 1974, my grand challenge was to figure out how to harness my ensemble of 64 binary thousand tightly coupled processors that shared nothing. That is, each processor operated its own operating system, and each processor had its own dedicated memory. My grand challenge was to figure out the intricate 1 binary million pathways of the email messages that I was sending to and receiving from my 16-bit long email addresses. My grand challenge was to visualize my new internet not simply as a new global network of processors that was mathematically embedded within the 16th dimensional hyperspace, but also as 65,536 tightly coupled processors that were connected to each other as one cohesive unit that is both a new supercomputer and a new internet de facto. That new internet that is a new supercomputer is a network of networks that was 16 networks deep, but yet in 3-dimensional physical space and in 16-dimensional mathematical space. That is, my grand challenge was to know a priori and know from my theoretical deductions that my internet connections were along 16 directions that were perpendicular to each other and that were in my theorized 16-dimensional hyperspace. My grand challenge was to discover that my new ensemble of processors defined a new internet. I discovered practical parallel processing as the vital technology that must underpin every supercomputer, and I discovered it before I could harness that new global network of processors as a new internet. As its first programmer, I had to understand my new internet as a network of networks that is 16 networks deep and thoroughly understand that invention before I could take the next step of programming the new internet to send and receive my emailed grand challenge codes and receive them at 2 raised to power 16 or 64 binary thousand processors. Each of those processors had its unique 16-bit long binary identification number that jointly served as its unique email address. As the first programmer and the first massively parallel supercomputer scientist, I did not learn the modern supercomputer that do many things at once. What made the news headlines back in 1989 was that a Nigerian supercomputer genius in the United States had figured out for the first time how to solve 65,536 real-world grand challenge problems and how to solve them at once and solve them across a new internet that is a new global network of as many processors. I, Philip Emeagwali, was that Nigerian supercomputer scientist that was in the news back in 1989. After 16 years, I knew the positions of the processors that defined the Philip Emeagwali internet. I knew them, both forward and backward, and I knew them along 16 directions that were orthogonal to each other. A secret source to my recording of the world's fastest computation and to my inventing of the fastest parallel supercomputer is that I discovered how to preserve the proximity of my 64 binary thousand supercomputer codes to the proximity of the corresponding initial boundary value problems of extreme scale computational physics. I discovered how to preserve that proximity and how to do so, and I discovered it when I mapped codes to tiny computers called processors, and when I emailed those codes in a one code to one processor corresponded way. That is, I emailed 65,536 grand challenge problems in parallel supercomputing to as many processors. On the 4th of July 1989, I figured out how to email supercomputer codes so that real-world problems that were nearest neighbors on the earth and that shared boundaries were sent to processors that shared nothing, or tiny computers that were nearest neighbor on the surface of a globe in hyperspace. I thought of my one-to-one corresponded problem-to-processor mapping this way. My country of birth, Nigeria, has Cameroon, Chad, Togo, and the Atlantic Ocean as its nearest neighbors. For this proximity, the extreme scale general circulation model, that is a grand challenge problem of physics that is executed across my massively parallel supercomputer, must assign 16-bit long email addresses to Nigeria, to each neighboring country of Nigeria, and to the Atlantic Ocean that bounded Nigeria. My eureka moment occurred when I figured out that Nigeria's 16-bit long email address must differ in only one bit position from the email address of its nearest neighboring countries and the bounding ocean. Loosely speaking, I applied that same addressing scheme of 16-bit long email addresses that differed in only one bit position to all rivers, lakes, and oceans and mountains that I must account for within the general circulation model that must be used to foresee otherwise unforeseeable global warming. By the 4th of July 1989, I had figured out how to uniquely name each of my 64 binary thousand processors, or as many tiny computers, that outlined my new internet. I named my tiny computers recursively, not randomly, as I had presumed in the mid-1970s when I began my quest for the ensemble of the slowest processors in the world that I could invent as the fastest supercomputer in the world. My unique naming strategy that yielded my 64 binary thousand or 2 raised to power 16 unique 16-bit long names was as follows. I began with 2 ensembles of tightly coupled processors that shared nothing and that contained the same number of processors or tiny computers that had identical names. For example, my 2 ensembles of 32 processors were each named by 32 unique strings of zeros and ones. I append 0 as the first name of every 32 processors in the first ensemble, and I append 1 as the first name of every 32 processors in my second ensemble. I visualize those 2 sets of tiny computers as quote-unquote brothers. I call them brothers because I assign them different first names, but I assign them the same last name. Newspapers that profiled me when I won the top prize in the field of supercomputing and won it in 1989 gave me the nickname, quote-unquote, the African supercomputer wizard. I was called a genius because I was the first person to figure out how to program those 64 binary thousand tightly coupled tiny computers that shared nothing. What made the news headlines was that I figured out how to harness the potential or untapped supercomputer power of my 65,536 computers, tiny computers. I visualized those slow computers as encircling my internet and doing so in a manner that was metaphorically akin to my flying 65,536 grand challenge codes and to my flying those computer codes through as many tiny computers and to my flying them while I was blindfolded. My wizardry resided in the technological achievement that I did not need to see any of the 65,536 tiny computers that I used to invent the world's fastest supercomputer. I physicalized the world's fastest supercomputer, and I did so without using my biological eyes to see any of its processors, and I did so without using my fingers to touch any of its processors. Because I was programming a record number of processors and doing so blindfolded, I had to have some concrete metaphors that I associated to that never before programmed supercomputer hopeful that was a new internet de facto. I drew my metaphors from my life experiences. Back in the 1980s, I quote unquote mapped about my 32 closest blood relatives from the same house in my ancestral hometown of Onitsha, Nigeria, to the same house in my adopted hometown of Washington, District of Columbia, United States. If I had mapped each of my 32 relatives to 32 different states, they will not have the nearest neighboring communication that they needed to do well in the United States. That nearest neighbor metaphor inspired me to do the same with my ensemble of processors that was a group of 65,536 tightly coupled processors that were identical and that shared nothing, and that I viewed as one seamless, cohesive supercomputer. What made the news headlines was that on the 4th of July 1989, I discovered how that ensemble becomes the world's fastest supercomputer. I discovered how the fastest computer can be manufactured from the slowest computers called processors. I discovered how to map 32 real-world problems to 32 processors that were tightly coupled and that shared nothing. The general idea was to imagine Onitsha as comprised of 65,536 households and to move all 2 raised to power 16 households in Onitsha, Nigeria, into as many houses in Washington, District of Columbia, United States. I was in the news because I discovered how to move them in a proximity-preserving way that preserves the original nearest neighboring structure, namely, if Okonkwo and Okafor were nearest neighbors in Onitsha, then my nearest neighboring mapping would also preserve them as nearest neighbors in Washington, District of Columbia, United States. The word computer was first used in print 2,000 years ago. It was first used by the Roman author Pliny the Elder. The computer as we understand it today is the programmable supercomputer that was invented in 1946. In 1996, I was invited as an honoree to a celebration called the 50th anniversary of the modern computer. That celebration took place in Minneapolis, Minnesota. At that 50th anniversary banquet, a guest asked me, "Why were you honored for the development of the computer that was invented before you were born?" I answered, "My contribution to the development of the computer was that on the 4th of July 1989, I discovered the massively parallel supercomputer that is faster than the vector processing supercomputer. That is, I discovered the modern supercomputer of today that will become the modern computer of tomorrow. I discovered how to solve the grand challenge problem of supercomputing. This supercomputing problem was called a grand challenge because it was very complicated to solve it across a new internet. I visualized that new internet to be outlined by thousands or millions of identical processors, each akin to a tiny computer. That grand challenge problem was a century-old problem in mathematical physics. That grand challenge problem was in part published as science fiction by Louis Fry Richardson back on February 1, 1922. The January 11, 1946 issue of the New York Times loosely restated that grand challenge problem as a futuristic technology that would enable 100 computers to forecast the weather all over the world and to solve the toughest problem arising in mathematical physics. That New York Times article suggested that in the future, and I quote, the United States would be divided into blocks penetrating into the stratosphere. End of quote. Fast forward 43 years to the 4th of July, 1989. I invented how to divide the United States into 64 binary thousand blocks, each penetrating into the stratosphere. I discovered how to achieve a one-to-one mapping between those blocks and the as many tightly coupled commodity off-the-shelf processors. I figured out how to reduce 64 binary thousand days or 180 years of computing to merely one day of supercomputing. I discovered a new way of thinking about the new fastest supercomputer and about the supercomputer of tomorrow. I thought of it not as a computer per se, but as a new global network of tightly coupled processors that is a new internet and a virtual supercomputer. It is likely that Albert Einstein, who was then 66 years old and living outside New York City, read that supercomputer story that was printed in the January 11, 1946 issue of the New York Times. My supercomputer discovery that occurred 43 years later and on the 4th of July 1989 was the new knowledge of how I harnessed a new global network of identical processors or tiny computers that encircled a globe and harnessed it as a new internet. I discovered how to use that new internet to solve the toughest problems and the most important grand challenge problems that arise in extreme scale computational physics. That supercomputer discovery was science fiction to Albert Einstein. Thank you.
Insightful and brilliant lecture.
Thank you.
Insightful and brilliant lecture.